All right. Hi, everyone. So we're going to get started. It's my great pleasure to host Jason Liu. Jason is a PhD student from Brown, and he's working with Stephanie Telex. He's working on some really cool work on understanding things at the intersection of language and robotics. A lot of the work that Jason's been leading, in particular formalizing requirements in the form of temporal logic, is something that we've been really excited and inspired by, and we've been building on top of that. So we're really excited to hear more about that. So Jason's also has the privilege of being an NSF GRFP awardee, so which is like a big honor. And he's hoping to graduate soon. So we thought it would be great to get to give a talk about what he's working on and learn from this. Okay. So welcome, and please take it away.
Thank you. Thank you everyone so much for coming. And I just want, before I get started, I just want to say thank you to you for the opportunity, and thank you to the call for scheduling all the meetings. Yeah. So I'm Jason from Brown University, and yeah. So I'm mostly working on robot and language. So today I'll be talking about robotic language grounding. What I think is the first step towards developing robot that can use natural language. Yeah, so my research is mostly driven by developing assistant robot that can help people. And I imagine a future where personal assistant robots are very universally accessible, so we can see robots in everyone's home. This video shows a PR1 being teleoperated to perform many household chores. For example, tidying up living room and vacuuming the floors. So, and how do we convey those tasks to robots? We have many interfaces to program robots, and each of them have their pros and cons. Here I just list a few examples. So first, we have graphical user interface or touchscreen. It's very visual and intuitive to use, but it's not very flexible. Because to command robot to grab something or to go somewhere, we have to manually specify the red pose. The same thing with maybe space comps. On the other hand, we have code, which is very expressive and flexible, and also unambiguous. But it requires a lot of expertise to use. And then we have natural language, which is a great way to communicate with robots. It's expressive, it's flexible, ambiguous, and also easy to use for non-expert users. So because we humans use natural language, talk to each other all the time, when we deploy robots in people's homes, the most natural way to communicate with the robot will be through natural language. And with the help of large language models, we would want to develop a robot that we can just talk to like another person. So language is great interface to communicate with robot, but how come we don't have language we can already talk to? What are some of the challenges of using natural language? First will be natural language is very unambiguous. So almost all the natural language commands we give to robots can be ambiguous. I just give a very simple example here. If I tell the robot go to the restaurant on Main Street, but there could be two restaurants on the Main Street, McDonald's and KFC. So robot needs to know which specific restaurant we want it to go to. And also, natural language is very complex. For example, I can tell a robot to visit the bookstore on Main Street only after going to a Chase Bank. And after you enter the bookstore, move slightly to your left, find the orange magazine on the brown bookshelf in front of you. So it's very expressive piece of command that specify a long horizon spatial temporal tasks at the different levels of granularity. And it's also compositional, which in this case, it has some referring expressions in this command. All those things we can leverage to define maybe a representation we want to use to ground natural language too. So in this example, the referring expression will be the bookstore on Main Street, the Chase Bank, an orange magazine, and the brown bookshelf in front of you. So we can maybe give us some hint of how we can process this complex language, which could be decomposed into substructures and process them separately. Another challenge is language must be grounded. For example, I may ask robot to fetch me the orange cup in front of you. because robot operates in the physical world, and the command we give to the robot must also be grounded in the physical world. So in solving natural language grounding problem, we would want to address all those challenges I just mentioned. Robot, just to quickly define language grounding in this context, would be mapping words in a sentence to a robot's decision process, either perception space or action space. Even with the advance of foundation models, this problem is still very hard because we want to model uncertainties in both humans' mental state and also the environment. And to answer this, to solve this language grounding problem for robots, we want to answer two questions. First is what grounding representation we can use. And then once we decide the grounding representation, how we can ground to this representation of choice. And in this talk, I'm gonna try to answer those questions. And also, we'll see some robot understanding some complex natural language commands. For example, a spatiotemporal command like go to the white car near dumpster exactly 3 times. In addition, avoid the stairs in front of the apartment for a navigation task. And also fetch and delivery task, go to the wet desk, but only after the kitchen counter. For example, maybe you want to grab the juice from the kitchen counter. And those tasks are very hard because they are long horizons, which means they can be decomposed to many subtasks, and they specify they need a specific temporal ordering of the subtask to be able to solve this the final task. And we want to do this in 0 shot without retraining on any language data. Okay, so in this talk, I would first like to propose a way to ground natural language commands from humans to a structured task representation. And presenting 2 works in this category. One is grounding temporal command in normal environments. Another one is grounding spatial temporal commands in normal environment. And then how we can, I'm going to present another work and to show how we can leverage the structured representation to transfer skills robot learn to solve novel tasks 0 shot. And the work I'm going to present here is called LTL-Transfer. And finally, we'll talk about the survey paper recently did with Stephanie, Vanya, and Ray on how we can ground various language to various grounding representation using large language models. Okay, so the first work I'm going to talk about is LTL-Transfer. It grounds temporal commands in normal environments without retraining on language data. This would give us the capability of unboxing any drones, any city, and starting giving so we can start understand commands provided with the semantic map and the motion planning capability. And we tested this system in 21 novel cities and deployed it into indoor environments. And because we leverage this structured representation, robot will be able to abort execution when they detect infeasible commands. So okay, so the first question I want to answer in this lab work is how to what grounding representation to use. And to answer this question, maybe we can think about some of the desired properties we want this grounding representation to have. First, like I mentioned before, we would want the representation to be unambiguous. So this representation can unambiguously and precisely capture natural language given by human. We also want this representation to have the expressive power of natural language. So some of them will be be able to capture temporal constraints. For example, this natural language command, go to the bookstore first, then the coffee shop, and always avoid downtown. There's a temporal ordering of subtasks in this command. And also we want to be able to capture spatial constraints. For example, put the fork on the left side of the plate. And then because natural language is compositional, we would want our representation to also be compositional. So we can decompose the natural language and ground each part of natural language to a different part of the grounding representation, and then process them separately. And another thing is because we deploy robots in human environments, we want this representation to provide specific guarantees. For example, we want the robot to detect when a given task is infeasible or the execution violates some given constraints. One possible choice of representation would be linear temporal logic. It's a it was so LTL for short. It was invented by Bernoulli in 1970s, and we want this representation to capture all the natural language commands the human user can give to robot, and the LTL can represent a large portion of those natural language commands. In fact, a survey paper in 2019 showed that 245 robotic tasks from 306 papers can be expressed in LTL. So in this talk, I'll be using LTL as the representation, grounding representation of choice. So I'll go through the semantics or the syntax of LTL using one simple example. So for example, we give this natural language command to robot, go to Walmart, but only after visiting Chase. You can ground this natural language command to this LTL formula, finally Walmart and not Walmart until Chase. And different part of natural language, this natural language command can be grounded to different part of LTL formula. For example, go to Walmart can be grounded to this phrase called finally, F for finally Walmart, which means at some point in the future, we want to go to Walmart. And the second part gives more constraint on this trajectory, which means before going to Walmart, make sure you visit Chase. That's what the not Walmart until Chase means. And LTL is very good at capturing those kind of non-Macrobian, non-horizon kind of tasks, which would be hard for numerical rewards. And then we can, once we have the LTL formula, we can translate this LTL formula to a Bucci automata, which is state machine keep track of the task progress. And then transition in the environment on the right would induce transitions in the state machine. So for example, as robots moving to a Chase bank, if in the environment, the state automata would transition from state 0 to 1. And as robot move to Walmart, the automata would transition from 1 to 2 and finally reach the goal. Okay, so we decided to use grounding LTL as grounding representation, and how to ground those language to those grounding representation. I'm going to answer in those two papers. The first one grounding temporal command, the second one grounding spatiotemporal command. And some of the assumptions I make in those works are first, we assume the environment is static and fully observable, so the robot can keep track of its own state and knows this, the location of the landmarks. And we will assume we have access to a predefined set of propositions and the semantic information about these propositions. So for example, a proposition Walmart could be described by a piece of text in a serialized form like JSON. It contains the address of the landmark, also the amenity of the location. It's a supermarket. And then another proposition, car could be described by an image of a red car. And we can grab this information online either from OpenMap database or Google Street View. And then I assume we have a labeling function, which given environment state can map to the propositions that are true in the current environment state. So for example, if the drone is hover over the Walmart, we know the proposition Walmart is true in this particular state. Okay, and then just to formally define the proposition solve for the first piece of work, land to LTL, we assume we take as input temporal navigation command and also semantic map, which include the propositions, also the semantic description of these propositions in terms of text. And we want to generate an LTL formula whose propositions are grounded to real world landmarks. Okay, so given a complex piece of command, go to the store on Main Street, but only after visiting the bank. And also we have access to a semantic map, which describes the propositions using some text. we want to generate this grounded formula, finally Walmart and not Walmart until Chase. So we decompose this complex task of processing this language into some subtasks. The first one is we want to recognize some of the referring expressions in this command. So in this case, the referring expression will be the store on Main Street, also the bank. And referring expression in this context just means the noun phrases or proper nouns referring to some landmarks. So in this case, the store on Main Street in this environment would refer to Walmart, and the bank referring expression bank would refer to Chase Bank in this environment. To solve this task, we used in-context learning with GPT-4. So we feed in some in-context examples and query to GPT-4, and it outputs the correct, it extracts the referring expression from the input command. Okay, so once we extracted those referring expressions, we want to ground those referring expressions, those texts, into propositions in the semantic database we have, the semantic map we have. To do that, we first use the text embedding feature of the large language models to embed the referring expressions. Also, we use the same text embedding feature to embed the semantic descriptions of the propositions to the text embeddings. And then we just use the cosine similarity to find the best matching. So in this case, the store on Main Street will match to Walmart and in the semantic database. And the bank, the referring expression bank, would map to Chase in the semantic database. And then we want to assign symbols to those grounded landmarks propositions. And then we can replace the referring expression in the natural language command by the symbols. So the store on Main Street will be replaced by symbol A, and the bank will be replaced by symbol B. So this would make the later on the translation task easier to solve because it doesn't need to recognize the referring expression anymore. It was taken care of by the referring expression recognition module and later grounded by the grounding module. So now the lifted translation module only to translate this lifted command to a lifted formula to finally A and not A until B. And because we already have the grounding for those symbols, we can just swap back the symbols by the propositions. And we find a small large language model to solve this task. And then finally, we arrive at this grounded formula, finally Walmart and non-Walmart until Chase. And once we have this LTL formula, we turn that into a Boucher automata and use that to provide the reward signal for our downstream planning algorithm or reinforcement learning algorithm. Cool. And because we want to deploy the system in any normal cities, to test the generalization capability of the system, we also designed a few tests going from a easier task to a harder test. So first is the first test we designed is alternate holdout. So during training test, the robot would have seen all the possible formulas, but the language description of those formulas are different. So for example, during training, robot may say the pair of examples go to Chase and then grounded to finally Chase. And during test, it was different natural language command that wasn't seen during training, but it's grounded to the same formula. So in this case, visit Chase. And the slightly harder test is called formula holdout. So during training, robot has seen a large majority of formulas, but some formulas with slight variation it hasn't seen during test. For example, in this case, finally Chase and finally Chase and finally Walmart is already seen during training, and this finally Chase and finally Walmart and finally Subways was not seen during training. And the most difficult tests will be type holdout. That means we hold out certain type of LTL formulas, which include maybe some unseen, which include some temporal operators. In this case, the training formula is finally Chase and finally Walmart. And during test, the robot hasn't seen finally Walmart and non-Walmart until Chase.
Quick question.
Yeah.
On the middle one, on the center, what does it mean finally Chase and finally Walmart?
Oh, yes. So this command means the robot can go to Chase or Walmart in any particular any order.
Oh,
Yeah,
so the finally doesn't mean the final destination, because it couldn't be both at the same time.
exactly.
Okay.
That would be one with one finally operator, but in the parentheses we have Chase and Walmart.
Shouldn't be or?
In the LTL syntax, this is this is how we represent this task.
Okay.
And then for the bottom,
Thanks.
yeah, and for the bottom one, it's a nested finally, which means we want to reach Chase first and then reach Walmart. We must reach Walmart after Chase. Actually, finally Chase and finally Walmart nested means we want to reach Chase and then Walmart, but we can also it's possible to reach Walmart before Chase. Okay, so once we design those tests, we tested our lifted translation module against some baselines. So we have fine-tuned T5 based models compared with some prompt pre-trained large language models. We can see when the robot sees all the possible commands and all the possible formulas, just have different variation of commands. The fine-tuned models perform much better than the pre-trained model. But as the unseen formulas increases, the pre-trained model start to work better than the fine-tuned model. We should think it's because when we fine-tune a model, the robot can only generalize within this distribution. So it can only recognize the type of command it has seen during training. The command and formula it has seen during training. And doesn't generalize while true the command hasn't seen during training, which will be the case for formula and test result. And then we also evaluate the full system using average success rate on around 2,000 semantic diverse commands from 21 novel cities.
So what type of fine tuning are you doing there for the LLM?
Yes, so to fine tune the lifted translation module, we construct a data set of lifted command with lifted formula on the bottom. Yeah, and then just do supervised learning. All right. So a previous state-of-the-art model that does generalizing generalized language understanding to normal environments doesn't perform very well in our environment. It was fine-tuned on a very small data set. It's also an encoder-decoder GRU model with attention, a relatively small model. And also we use a prompt pre-trained large language model to solve the whole task going from natural language command to grounded formula. Also doesn't perform quite well. But with our modular design, which leverage large language model in different part of the system, can perform much better than the baselines.
Question. So could you explain a little bit more what the prompt GPT-4 mechanism is? So you're giving it a few short examples of natural language and just LTL formula, or what do you do?
Exactly. So we would first give the task description of what we want the large language model to do. Your task is to translate this natural language command to a grounded LTL formula, and give as many in-context examples as we can, a pair of natural language and LTL grounded LTL formulas in this context window, and then just feed in the correlate natural language command. And also provide with these available propositions the large language model can use.
Will you show some examples of when it fails, why it fails?
I can show. Yeah, I can show it after talk.
Okay,
I don't have it.
that's fine. Okay.
But yeah. So the reason why it fails is because sometimes it wasn't able to recognize the referring expressions. So by decomposing this the complex natural language command to sub parts and process them separately, it helps us outperform the prompt GPT-4 model.
When you say that your system fails, okay, there are two types of failures. One is that the goal may not be achievable at all, in which case you don't expect the system to be able to provide the answer, right?
Right.
The other type of failure is that in fact you give the wrong answer. So when you say fail, which one is it?
Yes, I think later I'm going to try to break down all those failures in in some failure cases, when we deploy system in the real world. But yes, we would able to capture when the input command is infeasible, because we cannot solve this command, and this we can capture with this structural representation. And then if there's error in the representation, like syntax error, we can also capture them. But if there's semantic errors, so it generally correct LTL formula, but it doesn't match what the natural language says, this type of failure we actually right now can't capture. To solve this problem, we're thinking of doing some program synthesis, which would actually have a feedback loop from robot to human, call a human, ask some clarification questions. Thank you for the question. Okay, so first I'll show one success demonstrations of the robot in the real world. So in this case, visiting a wooden desk exactly 2 times. In addition, do not go to the wooden desk before the bookshelf. So we would want to visit the bookshelf first and then go to the desk twice. Maybe we want to try to deliver some books. Yeah, so the robot would first navigate to the bookshelf, which highlighted by the green paper on the floor, and then navigate to the wooden desk, highlighted by the purple paper on the floor twice. Yeah, so we deployed the same system without modification in 2 indoor environments to solve about 58 robotic tasks, and just provided with the semantic map of the environment. Yeah, and then we talk about some of the failure cases we can capture. So first, robot will be able to capture infeasible tasks and abort execution. So in this case, go to the counter but never visit the counter. There's some contradictory in this task robot can capture. And the robot knows, okay, this task is infeasible, so I'm gonna stop executing. And then there's another task, find the kitchen counter in addition to avoid the doorway. For example, maybe the doorway is the only way to get to the kitchen counter. There's some environment constraints. This command valid, and robot will also be able to capture this and abort execution. Yeah. Okay, so I just talked about the first piece of work grounding natural language to structured representation, which ground the temporal commands in all cities, in both indoor cities and also indoor environments without retraining on language data. And the robot will be able to abort execution if it detects infeasible commands. Okay, so the next piece of work is called LTL-2. We extend the previous work to capture not just temporal command, also spatial temporal command, and also in novel indoor and outdoor environments without retraining on language data. And the spatial temporal language command we can capture contains 47 temporal patterns, also 19 spatial relations. And in this work, we also use multimodal semantic description of the propositions. In this case, will be as we have text as we had before, also images. Yeah, and as the input will be spatial temporal navigation command, also semantic map, where the proposition are described by both text and images. And we want to output this the same as before. We want to output LTL formula whose propositions are grounded to real world landmarks. Yeah, so now the input command is more complex. It contains spatial temporal constraints. So in this case, visit a vegan restaurant west of the bakery. Only then go to the red car to the right side of the bakery. And then the semantic database also contains multimodal description of the propositions. Here, the proposition plant city and wallflower are described by text, and car 0 is described by an image. And we also want to output the grounded formula, find car 0 and not car 0 until plant city. So we will take a similar approach. We'll decompose this complex natural language into a subpart. The first part we recognize is spatial referring expression. So in this case, spatial referring expression would mean referring expression that are connected by a spatial relation. And then we ground this spatial referring expression, or we translate this spatial referring expression into a spatial predicate. In this case, we a spatial relations connected by two of the referring expression. For example, the big restaurant west of the bakery is translated to the spatial predicate west with the vegan restaurant and the bakery. And similarly, the red car to the right of the bakery is translated to the spatial relation right, and also two referring expressions, the red car and the bakery. Yeah, and then those referring expressions map to the landmarks in the environments. In this case, the vegan restaurants will be mapped to the plant city, and then the red car will map to the red car to the right side of the bakery will map to the red car. Still, we use in-context learning with GPT-4 to solve this spatial referring recognition task. And then once we extract the referring expressions from the input command, we want to ground those referring expressions to landmarks in the environment. We apply a similar approach where we use text embedding to encode the text description of the propositions. And then we use the vision language model to transcribe the image description of the propositions through a piece of text description, and then use text embedding to encode that text description of the image. And then use predecessor to find the best matching. And in this case, the vegan restaurant is grounded to plant city, and then the bakery is grounded to the proposition of wildflower, and then the red car is grounded to the proposition car 0. And once we have those referring expression grounded, and how do we know two grounded landmarks actually matches the spatial relation? So we use the spatial predicate grounding module to solve this problem. So for example, if we have the spatial referring expression, the red car to the right side of the bakery, and also spatial predicate right, the red car in the bakery. And here the red car is grounded to that red car in the environment. Also the bakery is grounded to a wildflower. We would draw two vectors, one from the wildflower to the robot, another one from the wildflower or the bakery to the red car. As long as this arrow from a wildflower to red car lies in the half circle on the right of this green arrow, we know these two grounded landmarks actually fulfills this spatial predicate. Okay, so now after we extract the referring expression and grounded their referring expression, and then finally grounded the spatial predicate, we eventually grounded spatial referring expression to propositions. In this case, the vegan restaurant west of the bakery is grounded to plant city, and the red car to the right side of the bakery is grounded to car 0. And then again, we assign symbols to those grounded propositions. And then we replace the referring expressions in the input command by symbols, and then apply the similar lifted translation module we had before to translate those lifted commands to lifted formulas, and then swap back the grounded propositions. And then this grounded formula can be used as the reverse signal for downstream planning algorithms or reinforcement learning algorithms. And we, yes, sir.
You have some sort of like backtracking module here, or like if the spatial predicate grounding fails, you just like abort. Like if you have like the red car and then you check and it ends up not being to the right, but like to the left of the bakery, like is there a way to go back and see maybe there's another red car that you could have sold?
Current system doesn't have this capabilities, but yes, as I'm going to talk about some of the future works, we're thinking about having this feedback loop from human to robot. And if there's any uncertainties, we would ask clarification questions. Robot would ask clarification questions to them. Yeah, so we evaluate each module separately. So in 4 different cities with increasing number of landmarks. So as the landmark increases, similar landmarks with similar description may appear. So the first is a spatial referring recognition module. It performed universally well in all those different cities with their increased number of landmarks. So yes, large language model is very good at recognize certain part of the input command. And then the referring expression grounding module. So the performance actually decreases as we increase number of landmarks where there are similar descriptions of this referring expression, or similar descriptions, landmark with similar descriptions have been mapped to the same referring expression. But as we increase the number of candidates from 1 to 5 to 10, the correct grounding within those candidates actually is the accuracy is pretty high. Which is what we fit into the spatial predicate grounding module. We would fit in the top 10 choice of the referring expression model into the spatial predicate grounding model, HPG, which can use all the candidates to find the correct spatial predicate grounding. And as we provide possible candidates, more possible candidates, the spatial predicate grounding model can perform quite well in all different cities. And for the lifted translation module, we tested the fine-tuned model we used before, the fine-tuned small large language model with another technology called retrieval augmented generation with 10, 50, and 100 in-context examples. As we increase number of in-context examples, the performance of RAG increases. But as we max out the context window, the performance didn't catch up to the fine-tuned model. But I think we see a path forward. Instead of fine-tuning our own model, we can construct a data set and then use retrieval augmented generation to solve this lifted translation translation problem. Okay, so for the post-training evaluation, we use average success rate and tested on 20,000 semantic diverse command in 4 cities, 5 cities. And we also did a validation study with only image description of the landmarks, also text description of the landmark. It doesn't perform as well as using both image and text description. Because this multimodal semantic database can kind of describe the landmark that a single modality doesn't have the capability to capture. And then we also deploy the same system in both indoor and outdoor environment. Here I'll show you one example of this natural language command: go to the white car near the dumpster exactly 3 times. In addition, avoid the stairs in front of the apartment. Yeah, so the robot will take a loop around the apartment to avoid the stairs, and then go to the downstairs exactly 3 times. Yeah, here what we did is we provided the semantic map to the robot, and we also used the off-the-shelf motion planning algorithm to move between landmarks. So yeah, it's just gonna go back and forth 3 times. Yeah, and then we also deploy the same system in both indoor and outdoor environments, and just provide with semantic map of the environment and the motion planning capability. Yeah.
So I asked you the earlier question, which is that, okay, if the planner says that, oh, I mean, I cannot do it. So there are 2 possibilities, right? One is that there's really no way to do it, it's impossible to do something. Or otherwise, okay, maybe the algorithm is not clever enough to figure out the way to do it. So when you give me those results, in which cases refer to impossible to achieve, and what cases refer to it can be achieved, but the algorithm is just not strong enough.
I see. I understand the question. The first one is the planning. I kind of figure out, oh, there's no plan going from initial state to goal state. But the second one is the algorithm just doesn't know it. Couldn't figure out the plan. Is that it?
So there's a difference between those 2.
Yes, we'll be able to capture the first one. So if we cannot find a path from the state machine, from the initial state to the goal state, we can capture. But the second one, the current approach wouldn't be able to capture or recognize.
So you're acting in some sense, you're unfair to yourself, right? Because it's something that cannot be done, then obviously you cannot expect your algorithm to be able to do.
Sorry, can you down?
So if you set a goal, okay, right, and you ask the algorithm to produce a plan to satisfy the goal, right? Okay. So if the goal cannot be satisfied at all, right, then you should not be blamed, okay? Your algorithm should not be blamed for not being able to find the plan, right? Okay, but it seems that you're lumping those two types of failures together. So in some sense, so in this way, you're hurting yourself. Actually, we cannot blame you for not being able to do something that cannot be done.
So we actually separate the grounding natural language to the structural representation is one piece, and then planning algorithm is another piece downstream path. So the grounding part, grounding natural language to the structural representation, the structural representation can actually capture whether or not the input command is feasible or not. And this work is not focused on whether or not the planner can generate a plan, whether we can detect that. This library grounding piece of work doesn't focus on the feasibility of planning. If that answers your question.
I have a quick question about task itself. Was there exactly something that you actually needed, or did you try with? I mean, the task is slightly confusing to me. I think if as a human, someone would tell me that I don't know what is to go 3 times to the white card. You know, so I don't know how you measure if it's successful or not. I'm a bit kind of like trying to understand that.
So this is one type of temporal pattern we have in our training set or test set. Another one is like go to the place at most 3 times, or go to the place less than 3 times.
I think
So
that's
how do I
quite
schedule?
exactly what the modifier that you were. Okay.
Exactly. The exactly is just one demonstration we show. Also in the test, we also have other type of temporal patterns.
So, question, in the context of this generation, do you provide any other additional information about the background of this task? Like it's supposed to be doing a patrolling operation or something?
Not beyond this natural language command.
Okay. Because, I mean, as Roberto was saying, like when you say go to the dumpster exactly 3 times, that also kind of implies you got to go away from it.
Yes.
Now the question is, where are you going,
Yeah,
right?
exactly.
So is it like you go to the white car and you step away 1 step and then go there again, or do you have to like go? How far do you have to go to consider a step?
So
Yeah.
in this case, we would go to the nearest waypoints in this semantic map.
Okay, so that's what I'm trying to understand. Like, did you provide these other alternative waypoints to the system so it knows where the alternatives that it could go
Yes,
to?
we will provide the semantic map or
Okay.
the topology map to the rule.
Okay, I see. So it could use the semantic map to understand it should go somewhere else.
Exactly.
Okay, I see.
And then for the patrolling task, LTL would they also be able to capture patrol before the location A and also location B like 3 times.
I see.
Yeah, this
Okay.
Yeah. Okay.
Ray has a
Yeah.
Oh yes.
Yeah, just one last thing is, all of your LTL is propositional. There's no like quantifier. So what if I said something like go to every red car? How would you handle that?
That's a great point. That's the limitation of using linear temporal logic. It wouldn't be able to capture quantifier like for all there exists. Yeah.
Isn't there a first order generalization of LTL?
Exactly. So one possible extension of this work could be incorporate those first order operators into LTL and then ground natural language to those.
So in this example, the car we're seeing on the screen right now is not the correct white car because it's not near the dumpster.
Right.
Does your semantic map already tell it that that's not the right car? Or does it need to like inspect that car to see if it's close to a dumpster before it determines whether that's the correct white car?
That's a great point. So right now it doesn't inspect the red white car, but in the future work we're thinking about if there's ambiguity, if there are 2 white cars in the environment, if the robot sees this white car in the semantic map, it could ask clarification questions or which white car do you want me to go to. But specifically in this case, this white car is not near a dumpster. So that's another way to filter this white car out.
Well, so like, does the robot have like a picture of the correct white car that it can then recognize in the environment?
Yes, it would have a picture of the red car, a white car near dumpster.
Not like a text description that it uses like an image recognition, it actually knows which car it's looking for.
Yes.
I have a question, but earlier, where you asked, can you fetch me the cup from the counter?
Mhm.
Remember that example
Yeah.
before?
Yeah.
It said, can you fetch me the cup from the counter? You remember that one?
Yes.
Did you use a grounding rule for it to understand that you were not only asking if it's able to, but that you were asking to actually fetch it? Do you have a grounding rule for that?
Oh, yeah, for the manipulation part, we actually just hard code them. Once you go to the location, you just apply this manipulation skills and then just grab the cop. Only the navigation part is the language grounding system only grounding the navigation part.
For the navigation, okay,
Yeah.
so can you fetch and please fetch and get me, they are all already by default synonyms?
By default, sorry.
Are those already synonyms by default?
Yes, so, yeah, in this where we don't really handle the manipulation part. If that answers your question. Yeah.
I think he was asking like, can you detect the difference between can you pick up the red cup and will you please pick up the red cup?
Oh, I see.
Are you able to pick up the cup versus please actually do it?
Yes, it should be able to capture those different type of natural language. It wouldn't be like a manipulation task, it would be like, would you please go to location A or can you go to location A? Those two type of commands can be grounded in the same LTL function.
But you need to introduce a new mode of operator, because there's a different modality there. Right, I mean, asking for, for a favor, okay, it's different from doing, usually and then. Those are two different modalities.
That's a good point. I think, yes, in terms of robot execution point of view, either way, they would want the robot to go to that specific location. So I think from that point of view, LTL will be able to capture both of those commands. So, and yeah, we also deploy the system into our other environments. To provide a semantic map of the environment. I have until 12. Yes. Okay, so I need to quickly drop out. All right, so another piece of work we did is LTL-Transfer. So we can leverage the compositionality of this structural representation to reuse learn policy to solve novel tasks. And then we can avoid execution if we detect, given the learned skills, the task is not feasible. So one quick example is if a robot learn fetch juice bottle and fetch textbook during training, it can learn to chain those two skills together to solve this long horizon task, fetch textbook first and then juice bottle. And the proper definition is given a set of training tasks and a novel test tasks, and also a set of propositions for known landmarks. We want the robot to output a sequence of skills to achieve this novel test task. And it has 3 steps in this algorithm. First is learning policy for state-centric options, and then decompose those state-centric options to transition-centric options, and then transfer the skills, those transition-centric options to solve novel task zero shot. Here, the state and transitions refer to the state and transition in the reward machine, not the environment. So one simple example is given this task, find a juice and find the desk, where we can go to juice and desk in any order. And given this great world environment, we can transcribe this LTL task to a reward machine, which help us decompose this long horizon task into subtasks, which encode in state 0, 1, and 2. And then we use our algorithms are compatible with LTL to solve the subtasks encoding in state 0, which means we'll go from state 0 to other state 0, either to state 1 or state 2, depending on the proximity of the robot to the objects in the environment. And we also learn policy for going from state 1 to other state 1 and then state 2 to other state 2. And then once we have the state-centric options, we transcribe those state-centric options to target specific edges in the reward machine. So in this case, the policy for state 0 is decomposed into 2 options, which target edge 0 to 1 in the same machine. Also, another option target edge 0 to 2 in the same machine, depending on the proximity of the robot in the to the landmark in the environment.
So there's a danger that actually people who write this natural language commands, okay, might not. So when you do the translation into LTL, right, so I mean, may not actually translate the intent of the natural language sentence. So for example, okay, if I want to say, okay, I want the robot to go to finally end up in a state, okay, where there's juice and also the state, okay, there's also a death also. So in other words, I want the robot to get itself to the state, okay, where finally you will have both the juice, okay, on let's say a couple of juice on the desk, right? Okay. But if you write this way, okay, and this can be satisfied, okay, if I look at the trajectory in the temporal structure or the linear logic, right? So if I find a path, okay, that will visit a desk with a couple of juice on it, right? Okay, but instead if I can find a path that goes to a place, okay, where there's a couple of juice, okay, and then if you keep going, okay, you will find the desk, right? Okay, then that trajectory will satisfy, okay, the formula. Right?
Okay, I have an optionality.
Because basically the formula says that, okay, I want you to find, okay, finally juice, right? So that means that, okay, well, eventually you hit a state where there's juice.
Yeah.
Okay, and finally death, okay, you hit a state where finally there's a death,
Right.
Okay, but if I hit the juice first and then leave the place where the juice is and go to the place where it's a death, right? Okay, then that trajectory will satisfy the linear temporal logic formula, right? But that's not what you want.
Given this specific task, that's actually what I want. I just want the robot to go to either juice or death in any order. If I care about ordering, I will use a different LTL formula. I'll give a different command. For example, I want you to go to the juice first and then go to death. It will be translated to a different LTL formula.
Not sure that, I mean, because it depends on how you interpret. I think how you do the grounding, okay, right? That can make a big difference.
I agree, yes. But that's why we try to capture as many temporal patterns as possible. So this is only one simple example. And later I'm going to show another nested family example. Yeah, okay. So yeah, so we in training we learn skills to solve those two training tasks. Finally book just mean get a book, and then finally juice, and then finally desk. Just mean go to juice and go to desk in any order. And then during test, maybe you want the robot to first go to the book and then go to the desk. We would look at those reward machine, the test reward machine, and recognize, okay, this edge from 0 to 1 in the test reward machine, we already seen that during training from the first training task. I would apply the skills we learned for this edge. And then robot would go acquire the book first. And then once we reach the test reward machine state 1, we recognize we need to achieve the second edge going from 1 to 2. And this edge actually occurred during training from the second training task. And we will apply the skills we learned from second training task. And then finally go to this.
But that is really the hard problem, though, right? Because I mean, try to for a certain model, okay, for a particular formula, okay, that's a really well understood problem, right? But when you do natural language processing, okay, to me, okay, I'm not a natural language processing guy, but I can understand that it's a very hard problem because of a lot of these types of ambiguities. Okay, you can translate a command into an LTL formula, right? And then try to use logic to construct a model for it. Okay, and then you turn it into, you ground it, okay, that's basically turn your algorithm, right? But the big difficulty is whether your interpretation, how you actually do a translation of natural language into the LTL formula, whether that is accurate or not. And that is a very hard problem.
Exactly. I totally agree. Just because the natural language is ambiguous, there's many possible groundings.
So how do you know that actually when you say that we use my system, right? So how do I know that in fact your system actually is really capturing what I intend to do?
That's a great point. So in the future work, I propose to actually have a probability distribution over possible groundings. And if the uncertainty is high, we would ask, robot would ask clarification question to a human. In this case, we would just output the arguments. But in the future,
My suggestion would be, I mean, I'm not asking you to solve a very hard problem, I mean, I mean, it probably take many dissertations to do that, okay, right? But it would be nice, okay, if you, when you present your work and maybe you can explain, okay, some assumption that you're making in order to produce the results. So for example, okay, right, if I tell you that, okay, tell Robert, okay, don't have lunch before you. So let's say don't have lunch before you go to Walmart. Okay, right? Okay. But then okay, let's say that you are already at Walmart. Okay, right? Okay. Then you know then should I leave Walmart? Okay, right? And then go back to Walmart. Okay, before I go to lunch, or because no, I'm already at Walmart.
yes, if you already at Walmart, I think LTL would also be able to capture that. As long as that at that point you haven't eaten lunch, that means you have already satisfied this constraint. But at the point, if you're at Walmart, you have already eaten lunch, that means you already failed this task. So yes, the semantic or the syntax of LTL will be able to capture that specific task. Yeah, there's some low-level details I just skip over, didn't have time to talk about. But yeah, that's in the syntax of LTL. Maybe I'll skip through the results and so talk about the survey paper. So yeah, so in this talk, I'm mostly using linear temporal logic as a grounding representation and talk about two words that can ground temporal and spatial temporal command to LTL. But LTL is not just like many of you have pointed out, LTL is maybe not the final answer. So what we can to figure out what kind of grounding representation we can use, we actually did the survey paper where we review and situated papers about robotic language grounding on spectrum from left, more symbolic type approach, where I have many defines discrete symbols which have ambiguous semantics, also have some variability and interpretability capabilities. And then to the right of the spectrum, where we just ground natural language to a high dimensional embeddings, which is continuous and has less structure, which require less human effort, and they can generalize to more normal environments. And we just have something in between, for example, grounding natural language to a predefined skill description, also natural language and image subgoals. Yeah, so I just in this talk, we just talk about this 4 pieces of work going from language grounding, and then how we can leverage that grounding representation to reuse skills to solve novel tasks in the same environment. I also did some robotic manipulation work during my undergrad for vision-based grasping and suction grasping. And some of the future work I think about addressing is instead of relaxing some of the assumptions. One of the biggest assumptions is using natural language as the interface. We can have a multimodal type of grounding. So instead of just using natural language, also use vision, demonstrations, and gestures. And also, we still want to have this safety guarantees provided by the structure representation, so we can have this safety at the task level, but also at the motion level, and the interpretability from for the robotic system, where we can predict failures, and if we cannot detect failure as a reasonable, explain it to user, and also eventually recover from failures. And then by having this feedback from robot to human, we can actually ask for some clarification questions to clarify some of the ambiguity in the grounding. Yeah. Thank you very much for your attention and asking all the questions. Really appreciate it.
Questions? I think Ray had a question about like potential future directions and like adding first order logic. Is this something that you're actually going to be looking into? Any thoughts?
Yes, I'm actually looking into a good logic representation that can capture as many languages as possible. Yeah, so going back to that Venn diagram, we want to push the boundary of type of language, natural language, the logic representation.
Cool. Other question?
Talk briefly about using like an off-the-shelf algorithm for going from like the LTL to the actual like movements of the robot.
You're right. So we would ground natural language to LTL. LTL would tell us all the possible landmarks the robot need to go to, and then we use off-the-shelf motion planning algorithm to go between the landmarks. Yes.
I guess I'm curious about that off-the-shelf motion planning algorithm. That seems impressive.
Yeah, so we use Spot, the Spot dog. So they have the off-the-shelf SLAM or motion planning algorithm is called a graph map. We share the same name from your use group.
I have a question about like the length of the instructions that you give to the robot. Do you guys have any ablations on if you give longer instructions, if that affects how well your fine-tuned language model can actually I guess ground in?
Yes, great point. So in the current work, we're only grounding natural language going to at most 5 different landmarks. As we increase number of landmarks, or the which affects the names of the command, will actually affect the lifted translation.
You see.
The performance will drop.
And can you fix that by in your training set, including longer examples, or does this problem just keep I guess manifesting itself? Like even regardless of how long your training examples are, if you just give a longer.
Exactly, you can always get all the distribution and examples. Yeah, we use 5 because like as we talk to each other, we normally don't use that kind of long command, like going to 5 different locations. Like 5 would be like maybe like max.
I have a question about like when you set up a benchmark about correctness, you make some assumptions that there is one way to define correctness, but in like ill-specified tasks, the way humans naturally do it, there could be many possible solutions. How do you set up a benchmark to handle a large variety and creative ways of being correct?
That's what I was hoping to talk to you about those benchmark data set.
Okay.
But yeah, it's only this generalization test only is kind of specific to our going from natural language to LTL handle tasks.
Okay.
Can it handle deictic words like over there or over here, things like that? Especially because, you know, lots of times humans use them with like pointing and gesturing. You say you want to try and get gestured in, but can it deal with something like there?
Exactly, good point. I think there's ambiguity of what here and there mean in this context.
Yeah.
So yeah, right now we're not handling those kind of things, but in the future, I'm actually working with another lab members on using natural language and gesture to specify target objects. So yeah, so gesture can clarify some of the ambiguities in natural language.
Okay. Why don't we take one last question before? Yeah.
So you have a set of in the LTL-Transfer, you have set of skill and you have a new task. And when I have a new task, how can I find a suitable skill to solve that task? Like you have a lot of previous learned graph, and then we have a new graph. And how can I find the suitable axis in the learned graph?
Great point. That's a detail of algorithm I skip over. So right now we let's just look at the reward machine graph. We look at the edges of the test task we try to achieve, and just use edge matching algorithm we define to try to find the some edges in the training task where we have learned options. If we cannot find those matched edges in the training task, we just say, okay, we haven't learned those options to solve this normal task. And then robot wouldn't take any random action, we just stop saying, I don't have enough knowledge about how to solve the task.
So do the matching algorithm take a long time?
We parallelize the matching algorithm, so we can run them offline for the training edges. So online it doesn't take very long.
Okay, well, thanks, Jason, for the wonderful chat.
There for the questions, invite you to take it offline.
Okay.